Okay, so lecture one, the transport equation. So in this lecture, we'll talk about what is a partial differential equation. We'll derive the transport equation, why most of the partial differential equations we'll see are mostly physical, and some terminology and notation. So a partial differential equation, just an equation involving partial derivatives of some function. The goal is to find the function, right? So it's like most differential equations. The big difference between partial differential equations and ODEs, or ordinary differential equations, PDEs involve functions of multiple variables, and ODEs are generally functions of one variable. So here's our first PDE. The transport equation is a first order PDE. So C in this equation is some constant. And the goal is to find U, which should be some function of both x and t. So where does this equation come from? Well, the idea is that you have a blob of stuff and it's moving somewhere, and you want to know how is it moving. So an example would be, suppose you have a stream of something. I suppose I should put in little waves or something here, right? And you have a velocity v, and the stream is going downstream, and it's pretty narrow. So you have a block of stuff in your stream, and this stuff is going downstream. So how does it go downstream? So where does this equation, why does this equation model this situation? So the idea is that if you think about a block, a physical block in the river, right? So the river is flowing, or the stream is flowing that way, v, and we set u of x comma t to be the density of whatever stuff we're looking at. And what we want to know is, how is this stuff distributed throughout the river as time goes on and as x goes on. So if we call this, right, x plus delta x, so here's our x plus delta x. What's the basic equation that we have here? Well, stuff in minus stuff out equals change in stuff in volume. So what's the stuff going into my volume? So that's the stuff, or if you're doing physics, that's the flux of stuff going in. Right, so flux is another word that you hear for that. So generally, right, we've got an area, delta x squared, and how much stuff comes in? Well, v times u of x comma t at a particular time t. Right, so what does this mean? I've got a face of this box. It measures delta x by delta x. U of xt is the density at each point inside there, and v is the velocity, right? So the density here, as it flows through, right, it brings stuff in there. And so the density times the velocity times delta x squared gives you the stuff in. Stuff out, which is the flux out, that's at the other face. That's stuff coming out. But same area times the velocity times u of x comma t. Oh, sorry, u of x plus delta x comma t. So we're making an assumption here that the distribution depends only on x as we're going along here. It doesn't matter, the y and z dimensions don't matter. So you have to think of it, if you think of a stream, it's like a clog sort of moving down with the entire stream. Great, so finally, changing stuff inside. Well, that's going to be u of x t plus delta t minus u of x t, right? So at a time, move it to a little time in the future, minus how much is in there now, times delta x cubed per unit time. So what is this? This is a volume. This is the change in density. So volume times change in density gives you the change in mass. This is the mass flowing in. This is the mass flowing out. This is the change in the mass inside. And so we want all these things equal to each other. So stuff in minus stuff out gives you delta x squared times v times u of x comma t minus u of x plus delta x comma t equals u of x t plus delta t minus u of xt delta x cubed over delta t. So let's simplify this a little bit. This delta t stays here. We can cancel this out and cancel this out, but we have to divide by delta x, right? Because we have a delta x squared there, delta x cubed here. The delta x squared cancels two of the delta x's over here on the right side, but then the third one will divide by there. And why do we want to do that? Well, this, if we take the limit as delta x goes to 0, this becomes v times du dx. And if you take this, right, notice the t plus delta t there, take the limit of that as delta t goes to 0, you get du dt. And this actually comes with a minus sign because I've got them backwards, u of x comma t minus u of x plus delta x minus t. And so this is that. So the du dx term, this is saying stuff flowing in minus stuff out. And this is the change in side, right? So it's conservation of mass is what it is, right? This stuff flowing in, this stuff flowing out. Let's see, I should have a dx here actually instead of a dt. Should be the same. Good. So a couple of points here. One, these kinds of, when we're setting up these kinds of differential equations, right? That kind of a thing will show up often. X plus delta x, t plus delta tt, divided by delta t, delta x, that's a partial derivative. Second thing is we're making some assumptions about our u of xt, in particular, here, right? We're assuming that u of xt is roughly constant over this very small volume that we're looking at. So that's putting a restriction on u, right? It's sort of assuming that it's continuous at the least, right? Because if you look at a continuous function over a very small space, it's essentially constant. So when we derive some of these equations from a physical consideration, there are approximations that go on that tell us something about the kind of restrictions we have to deal with the math, right? And here we have to say, well, u of xt is roughly constant over delta x cubed, which means that u of xt has to be a constant thing. We have to be able to evaluate these derivatives, right? So we need to have not just continuous, but we need to have derivatives, right? Du dt and du dx have to exist. But we will see more equations that look like this. We'll derive the wave equation, the heat equation, for example. So a lot of the differential equations are mostly physical because of a couple of reasons. One is, you can write down whatever differential equation you want, but most of them won't be interesting, right? So the wave equation, the heat equation are particularly relevant. And that this historical thing is in the 1700s when people started using differential equations to model the world. Remember that calculus is invented in the 1660s. It really gets sort of formalized by 1700. So most of our stock of PDEs are ones that arise from physically interesting situations. If you just write down a PDE, you won't be able to do much of it. The second thing is mathematical. If a PDE model of physical phenomena is a good model, then there's a solution because the real world tells you there's a solution. And the problem is to figure out the solution. So we like to use a lot of PDEs study things that come from the physical world. So a little bit of terminology notation. We will use subscript notation for partial derivatives a lot, just because it saves us some time. Types of conditions that we put on boundary conditions, initial conditions. This is usually connected to our variable t, which we usually interpret as a time because we are doing a lot of physical stuff. And boundary conditions, this is usually connected to x, and later in the course will be connected to y and z. And those are space conditions, right? So about a transport equation with initial conditions would be u sub x, where's my example? Oh, u sub t plus v u sub x, so there's our partial derivatives, equals 0, with u of x comma 0 equals some initial data. So this is at time equal to 0. The distribution of u looks like that. And then we want to know what happens as time changes. So that's initial conditions, time equals 0. Boundary conditions. Well, imagine that we have a channel that we're having water flow through, right? And it starts here, and not sure how I can draw this, right? We have water. Okay, we'll just draw a bad diagram. And then there's a pipe here that it goes into, right? So there's a boundary condition at L, right? U of x, nope, u of 0 comma t equals 0, because here is where everything, that's a wall there and everything is coming in there, so there should be no density at this point. And then u at 0 comma L, sorry, u at L comma t at the end of the pipe has to obey some other function, right? Because it has to go into this pipe. So, and that gives us boundary conditions saying at this point, there is no water because that's the wall. And at this point, at x equals L, there's a pipe or something that we have to take account of. So finally, how do you show that something is a solution to a transport equation with a particular initial condition? So the transport equation is u sub t plus u sub x equals 0. That's because c equals 1. And initial condition, u of x comma 0 equals x squared. How do you check that something is a solution? Plug it in. So is this a solution? Well, left-hand side equals partial derivative of x minus t quantity squared with respect to t, plus the partial derivative of x minus t squared with respect to x. What's that equal to, right? That's left-hand side. Derivative, partial derivative. So if we're taking partial derivative with respect to t, we're thinking of x as a constant. So this is just the chain rule, x minus t, and then differentiate the thing inside with respect to t. Derivative of x with respect to t is 0. Derivative of minus t with respect to t is -1. Same thing here. Now we're differentiating this thing, thinking of t as a constant. So the derivative will be 2x minus t times 1, because the derivative of x with respect to x is just 1. And that equals 0, which equals the right-hand side of my PDE. Okay. So it's a solution to the PDE. Does it satisfy the initial condition? So left-hand side should be equal to u of x comma 0, but u of x comma 0 is x minus 0 quantity squared, which equals x squared, which equals the right-hand side of my initial condition. So it's a solution. Hooray. So in the next video, we will see how to actually solve the transport equation.